Now we'll move on to the next session. That is the first scientific session of this conference. And this will be the plenary lectures. In this session, we'll have 5 lectures. This session is going to be moderated by Professor A.R. Rao. Professor A.R. Rao, by practice, an astrophysicist. He led the development of CGTI instrument. CGTI instrument he has showed that CGTI instrument has the potential capability of both imaging and polarimetry. And he also led, before CGTI led multiple payload development, SOX instrument, IRSP3, instruments on IRSP3 and RT2 experiment. Now I request Professor A. Rao to take over.
Very good. So after this wonderful morning session, we heard all about making of AstroSat and got a glimpse of scientific research from Deepankar. Now we are going to the teeth of the thing, some major meat of the thing. The first scientific session, we have 5 lectures, Annapurni, KP, Andrea and Ranjeevan Gula. And organizer instructed me to restrict the timing because otherwise 7 o'clock we'll have scientific session and the Bharatanatyam together here. So please ensure that 20 minutes you finish the talk. I call upon Annapurni now on the stage to talk about probing star clusters with the UAE.
Sure, okay. Yeah. So, I'll stick to time. Yeah. It's only daytime and stuff up and down. So good afternoon, everyone. I thank the organizers for giving me a chance to talk about this particular topic. What I plan to do is already the stage is set by Deepankar, so I'll jump into what is the science behind it. But my focus will be on star clusters and what insights we have obtained so far. And the first slide is an image of a globular cluster obtained from UVIT. And you can see the very nice clarity, resolution we have. And you may also see a very nice spiral galaxy, which is very far behind, but nice spiral arm seen. And also one more object over here. So there are a lot of background galaxies also appear along with the globular cluster image, which otherwise you don't even see it. So these background objects are not observed in the optical image because of crowding actually. So you actually see how many galaxies are behind a globular cluster itself. It's a very cute thing to do. So moving forward, just wanted to, since a general audience, I thought I'll put a general slide on what exactly is a star cluster and what are we trying to do here. So star cluster is a group of stars. You can see 2 of them here. This is a kind of a sparse cluster, but there's a lot of field. It is sitting in a field of other stars. So it's like a group of stars, but they have some similar characteristics, but they are embedded in the field of our galaxy. So the challenge is that they are at the same, we know that they are all at the same distance. They have similar, the brightness measurement is changing because of the different luminosities. They have the same age, same composition because they form from the same molecular cloud at the same time. So they have the same age, so same properties can be assigned to it. But the problem is identifying them from what is the member of this cluster. So which one is a member, which is not a member, has been a problem, and now it is resolved because of Gaia mission. If people are working on it, we actually know which are the membership. So we can actually pick out which are the member stars of this cluster and assign properties to it. And that has really changed the ballgame. That's not because of UVIT, but UVIT science could be enhanced because we know which is the member. Previously, I find some interesting star out there. The question is, how do you know that that star belongs to this cluster? Now, how do I prove it? So I know the kinematics now, so I can prove it. So that has enhanced our science with UVIT. And this is another, the first picture you saw was the globular cluster. But if you see the globular cluster in the visual, this is how you see it. You can see how dense it is. So very difficult to pick out single stars. But the previous slide, you could actually see how nicely you could pick up stars, right? So that is the advantage of UV. Now moving forward, what do you do with it? So if you take this cluster, same cluster I have put here, you plot the luminosity versus color in a basically a temperature in a diagram, you will see this evolutionary sequence. That is the test bed for understanding stellar evolution, how stars evolve. How do I know that the star is evolving? So these are the ways in which we can do it. This is a color magnitude diagram for an open cluster. But the same thing for a globular cluster is this. So you can see the number is very different. You have very large number of stars here. And each sequence you see the pattern is an evolutionary sequence, which tells you what is the physical process the star is going through. It is in the main sequence like the star, or a giant where it is burning hydrogen in a shell, or this kind of a star where it's actually fusing helium at the core. So there are horizontal branch stars, etc. So these are all part of the globular cluster. So they are fundamentally different, large number of stars in globular clusters and less number of stars in open clusters. Now, sorry, I think I'm going, yeah. So how do you know they can be used for stellar evolution studies? Because as the stars age, they leave the main sequence and become red giants. So as the turn of magnitude becomes smaller and smaller or less luminous, the cluster is old. That's how we can find out the age of it. And when it becomes old, the other stars like the remnants also start forming, like the white dwarfs. The white dwarfs are hot and less luminous, very difficult to detect. So the challenges are the following. If you want to study stars in a globular cluster, it's extremely crowded. How do you do? Only with HST. This is the 47-TAC globular cluster. You can see how crowded it is, but you can see this kind of a resolution in HST, Hubble Space Telescope. Now you see the colors of various stars in the same field, and you plot them on the color magnitude diagram, you can see that there are blue stars. Now these blue stars are in the central region. Now this kind of environment is where the stars actually can collide, because its stellar density is very high. And this produces very extreme amount of different types of stellar evolution which otherwise you cannot see. So if you want to detect them, you have to have HST, or you have to have other means. Now I'll explain how UVIT has helped us to detect these kind of stars. So the problem is the membership in the case of the open clusters, which we have surmounted with Gaia, but we also have the extreme horizontal branch stars, etc., which is happening in the globular clusters to be studied. So UV advantage is what I said, the crowding lifts up. So this is a image of visible and ultraviolet using HST. You can clearly see that this cluster, which is over here, this pointer is pretty time consuming, it just disappears because this is old star. So you can actually see the blue stars here. Same if you see a globular cluster here, you can see the difference in ultraviolet and optical. So you can pick out the stars, even though UVIT doesn't have that good resolution like HST, but it still can pick out the hot stars at the centers of these clusters. This is a great advantage. So moving forward, what you do with open clusters is that, as I mentioned, this turn off is what helps you to identify the age of the cluster. So these are the old cluster like M67, and these are the young clusters which have got the magnitude which are going up high. Now, as you know that the evolution demands that the cluster turns off and moves forward, and the stars cannot be moving here because the core shrinks and it has to become giants. So there's no way in which the star continue to be in the main sequence. So over here, what happens is this is a sequence a single star has to follow. Now, what happens to these stars? These stars are still present in the cluster, but they are cannot be explained by single star evolution because the star has to evolve to the red giant. But how did the star staying away? So these are the blue stragglers, and this is one of the mysteries which has been around, trying to see how the star is continuing to be on the main sequence when other stars are evolving off. What is special about them? People did not know. So the same with globular clusters. You see them here. These stars are all evolved off. But these stars, these are blue stragglers. This is one of the key areas where I have worked, and the teams who have worked in star clusters have revealed the formation mechanism of these blue stragglers. There's been one very interesting, impactful study which has happened. The second is in globular clusters. You can see this blue horizontal branch stars. Now you plot them in the UV diagram. This is the near UV magnitude from HST. You can see that this branch actually turns down. And you can also notice that this red giant becomes very faint, and the ultraviolet flux of these stars are very high. So you can actually handpick them. So this helps you. These are towards the center of the course of the globular clusters. So you can resolve these stars, pick them out, and study them. You can also study them. Now the question is, how do you study them, right? So if you go to them, so this is the cartoon just to wake you up in the middle of the talk. So this is a cartoon where one of my students, Sneha, had put together. This to say that to cut the story short, you have the stars, the blue stragglers are there. How do you know they're members? Now, I know that they're members, but how do they form? They have extra fuel. How do you get extra fuel? There are only three mechanisms. One star eats up the other through mass transfer. The other collides, as I mentioned, that in large systems where you have density, they can actually collide. This is a collision mechanism. There's another mechanism where there are three stars. So the third star spins around and takes the energy off. The central one actually merges, spirals in. Eventually, you get a binary system here. In this case, you'll get only one single star. So these are the mechanisms, but how do you know which color it takes, right? What is the formation mechanism? So how do you do it? So focusing on this here, so there's a mass transfer. This particular star has transferred mass to here, so you'll see a remnant. You can't resolve it, but it is an integrated flux you get. How do you detect it? You will measure the photometry, but how do you know that there is a companion sitting here? So you go onto the spectral energy distribution, you put the multi-wavelength data here, and you can start seeing that this is the expected flux, but this is the observed flux. So once you do the multi-wavelength spectral energy distribution, fit it with models, and then you get the excess flux, and you have another model to fit it. So you'll get two companions. Is that enough? No. You have to prove that these are physically possible. So you measure the temperature and radius of these two stars and put in an HR diagram. And that tells you the evolutionary status of the stars. So that is what we have done. And entire team has done, actually, all the teams involved. So eventually what I'm saying is that this is a star and B star in a binary system. When A evolves, transfers the mass to B, and the A ends up as a remnant. Now the question is, what is the nature of the remnant? People generally thought it was a white dwarf. Is it always a white dwarf? Nobody knows, because you expect it to be a white dwarf. But you need to measure it to find out that it's actually a white dwarf or not. Now, if you look at the HR diagram, where are the stars having? You have this main sequence stars, and the remnants all come here. So we know there are a lot of extreme horizontal branch stars, HDB, SDO, etc. But people think that they are binary pathways, not single star evolution. But we have to prove it. These are white dwarfs. You can see a big gap here. This is a gap region, but you can get filled up by stars here, but we don't know how they are formed there. We do see them. So going forward, there's also another set of stars. If you have two stars sitting here, one actually gains mass and only moves on to the main sequence. We discovered several blue lurkers, not blue stragglers. This remnant can again come down here. As I mentioned in the previous talk, this is the white dwarf. The gap area, there are many stars out here. Now, if you look at them, they are called ELM, the low mass white dwarfs. The low mass white dwarfs cannot be made with single star evolution. It has to be a binary evolution. Now, moving forward so this is the first paper we produced from UVIT. And so this was on NGC 188, and this is the same object we use for monitoring the sensitivity of the globular class, the UVIT as well. So we have been monitoring the sensitivity, and 9 years the sensitivity is actually been stable. So this is the first paper, and we actually see two components here. You can see the split. This is the observed spectrum, observed distribution. The single star can give you only this. So you have to add another star to it. So this is how we discovered that you can actually put it in place, and we developed systems. So summary, this open cluster has produced totally 23 publications, and this is one series we go with, URSC series, that has got 17 publications, and so many clusters are covered. There are many teams working on it, and many PhD theses, and some other students that also worked on it. So this is the M67 cluster. We have done a lot of work, and you can clearly see that of the 3 stars we have taken the blue stragglers. These two we did not find any companion, but you can see this axis here. This is the companion which we have found. Moving forward, this is another cluster where we see this is the blue stragglers here, and then there's a white dwarf, but we do see companions in white dwarf, but in between. So these are called low mass white dwarfs. They can be produced only by mass transfer. Low mass white dwarfs are nothing but the cores of their stripped stars. If you strip a sun-like star now and take the envelope out, what you get at the core is an ALM, a low mass white dwarf. So So is that enough? Can you complement with something else to understand the formation mechanism of blue stragglers? So we are moving forward to find out that there is a mass transfer, there's a star, and the donor is actually transferring mass to the accretor. What else can you know about the accretor? Can you detect the donor and make sure that the whole the chain is formed? Yes, we can. So if you actually have a binary mechanism and the matter is transferred, if the star is actually polluting the outside matter and the star is accreting it, you will see the processed matter. That is called, barium is such an element where you can actually get this is barium blue straggler. So when I say blue straggler is an accretor, it should have a polluted material. So this is an evidence that pollution has happened. So in summarizing, what is that we have understood? What is the main contribution of UVIT and this kind of a study in open cluster is that we have blue stragglers here. You can see all the clusters put together here. What did we see as blue stragglers and their companions? Blue stragglers are on the main sequence mostly, and some towards yellow stragglers and subgiants. But this is the white dwarf sequence. They're not sitting, some are sitting in the white dwarf, but not all are. So they're forming a sequence in between. And this sequence is coming from the strip stars. So we actually find a sequence in between the white dwarf and the main sequence due to stripping of stars. And this is also seen from about 5 giga-year cluster to about 200. This is a recent study which is published in A&A Letters this year. So these stars are shown here up. So you can actually see that it extends up to even to higher mass stars. So the strip systems form a sequence in between. So this is a particularly major contribution from UVIT as such. We also have, in collaboration with Pandey and Professor Kameshwar Rao, this is only cluster with a blue, very well known planetary nebulae. There are a couple of more systems, but that planetary nebula is not so famous. So this is an image where you have a cluster and the planetary nebula together, and we see the connection between the two and form together, I guess. Moving on to globular cluster. So there's a legacy survey conducted on globular clusters. There's a legacy program by AstroSat, and this proposal was part of it, and we have published about 6 papers under that, but 11 globular cluster data is public. I mean, the catalog is public, not the data. The data is anyway public, but the catalog is also public, and these are the teams who worked on it. This is the first legacy survey paper. You can see the difference in the images of the globular clusters of these compared to the optical data. Optical data, you can see the crowding over there, but you can actually see the crowding lifted up here. What did we understand? You can see that the combined color magnitude diagram, this is the horizontal branch. In the general, which I showed you, that the horizontal branch stars is actually not horizontal here, because in the UV, not the luminosity, but the temperature is what matters. So it becomes landing, but you expect the slope to continue here. The slope doesn't continue, but flattens. And using UV, it has been, with other models, we have proved that at this temperature at which the flattening happens, this is because of a physical process. So this is actually put together all the clusters together. The previous study, such combined CMD, was from Galax, and this is the one. This is chaotic, as not only because the data is not fully available, but because of membership. But Gaia has given us membership, is also HST. So this is cleaned up. You can clearly see the blue straggler sequence, horizontal branch, and the white dwarf. So a lot of studies are going on with this individual clusters. To be specific, 1851 was the first, Dipankar showed that image. This is the first cluster studied under with UVIT. We also have RL-array light curve, which is large magnitude variation in UV compared to in infrared in the case of RL-array stars. But again, more clusters, RL-array light curves have to be studied, because that's one area only UVIT can contribute, because there's no other far UV detection possible for RL-array. This is another cluster with RL-array. There's another important factor coming from the 2808 globular cluster. This is a very dense cluster. There are a few papers which have come out. But this tells you the kind of luminosity, the number of stars with luminosity, which can give ultraviolet flux, even old systems. If you look at even galaxies which are old, elliptical galaxies, you might get UV flux. Is it because of old population or new star formation happening here? How do we resolve it? We can put limits because we expect most of the stars to be in this band because that's the post-AGB evolution, but we actually see most of them in the post-Mank phase, which is an order of magnitude luminosity less. So this can put a limit on them. We also have studied the Omega Centauri, and this also has very interesting results. Moving on, there is NGC 362 has been studied by Ramakant Yadav from Aries and their group. I'm also part of it. They have found very interesting stuff with this cluster, particularly because this is a post-core collapse cluster. So if you look at the cores, you do see a lot of binaries, blue stragglers, and you also see blue lurkers. This is only one globular cluster where we have found the main sequence stars to have white dwarf companions. That's called binarity. And some white dwarfs also, massive white dwarfs, could be possible leading to progenitors of various types of systems which are now found in globular clusters. So that's also a very interesting result. So thanks for your attention. Time's up. I just want to add that the globular cluster data, most of them is public. We have studies are done for about 15 or up to 20, but a lot more data is there. Students over there, there's a little gold mine sitting there. There's a lot of data and tools are available. It's doable. Please, you're welcome to take it up and do it. I mean, all the data is public now. Yeah, thank you.
Thanks, Annapurni, for sticking to time. So we have some time for question and you need people to work. But what about the all analysis sequence that's completely streamlined? And anything further to be done in that?
No, I mean, in the sense that analysis people have to develop, the globular cluster is slightly tricky in the sense that each evolutionary phase, if you are trying to explore, then you need to build up your own models to understand it. Some simulations and models have to be understood. But basic, like initially when we were starting to do the SCDs or even the models, they did not have UV filters built into it. So we have to get the models and then ourselves get the simulated data and do it. That and all done now.
And available.
Everything is available in the website itself. So all that is integrated. So all the required model-based data for UV filters are all available now. So that's much easier. And also the SCD fitting technique is available in GitHub. It keep getting updated. And so you have error analysis, everything is there. In it's available in GitHub.
Very good, very good.
Nice to see those results from the legacy survey. Is that continuing or
it's continuing? So after the first set of students are over, we have said starting to reduce and put up the catalog for the next set of clusters.
Now, as a future program, you also had better spectroscopy capability. Where would this go? Just to get an idea.
Yeah, so in the ultraviolet, as I'm seeing, we have found differences in helium and etc. in the inner star, like the evolution of inner stars were not understood. The stars inside the core region was not understood. Now we have some understanding based on models, because you compare and make models out of it. Like in Omega Sun itself, we are getting 5 populations and we are able to fit them. But then if you want to spectroscopically say that this is actually happening, you need spectroscopy. Third thing is when you see this bending of the horizontal branch in the ultraviolet, that's because of elements which is coming up. So diffusion is happening because of at a high temperature and low, thin atmosphere on it. This diffusion brings up metals onto the top. So you have to fit it with a high metallicity models, but you have to prove that yes, it is. So you have to get spectroscopy. So without spectroscopy, this still will be like this, yeah.
Yeah. Was the X60 on when you were observing UV?
Yes, yes. 1851, we attempted to combine that and identify the...
So you must have observed many white dwarf in X60?
No, we tried to do in globular clusters, but then multiple sources were there. We weren't able to see which one would be giving that count. It was not possible to resolve. So we dropped the idea of including a 60 analysis. Yeah.
Thank you very much, Annapurni, for this wonderful talk.
Thank you.
Clusters, now we move on to specific white dwarf sources, cataclysm variables. Here we will talk about AstroSat-led campaigns for the study of CVs.
Yeah.
Okay, thanks again for giving me this opportunity. I'll be continuing from where Annapurni just left. Now talking about white dwarf systems in binaries and so on. And that is a kind of less trodden path in the community, especially in India. And it particularly looking at the future, I think the novae, which happen quite rarely in the white dwarf systems, are important. And we had covered quite a bit of them as targets of opportunity. So I think that looking forward in AstroSat, these are the areas of novae and deep legacy programs and so on. So I will, yeah. So, these so-called characteristic variables, novae are part of it. And there is a whole variety of them in which these white dwarf system exists, starting from, depending on magnetic field and other things. And these systems are very close to us, and they are excellent for studying accretion systems in, well-resolved objects and so on. And even though they are low luminosity, their nearness helps us to understand a lot of processes and so on. And among them, we have on the low field systems, we have novae, which are large eruptions of 6 to 10 magnitudes in optical. Then you have recurrent novae, which are some of few, and you are lucky to see them, and we did do with AstroSat. And then there are dwarf novae and so on, which are in various varieties shown here. Then there are nova-like variables. And then comes the one which are most studied, the magnetic CVs, which I had started with, but now I shifted more to the novae, and I'll talk more about the novae and a little bit about the, there are a lot of posters here on, and there'll be other talks on the CVs that we have done with the thing. So, okay. So, CVs, as I said, there are three, these are main types, non-magnetic, and so on, where you have accretion disk formed, and the magnetic field is not disrupting the flow. And then you have intermediate polars where we have truncated accretion disk, and then you have a polar which you have a stream of matter, and the disk cannot form because of very high magnetic field and so on. In novae are special, these are very close systems. These are very, very short systems, something like Sun and Mercury orbit, and there you have two stars rather than Mercury. And if you imagine that system sitting in the center, the two white dwarf, which is the site of explosion I show here, and then the matter accumulates, and there is a blast happening, and then you see this huge, massive blast that comes out, and which you can then study in through optical, X-ray, and so on. This is also the examples where you can actually put the multi-wavelength aspect of AstroSat in full use and so on, and we have done that. So what are the novae? These are binary system, white dwarf accreting from an ordinary star, which could be a main sequence or a red giant, or even a dwarf star. And this accumulation of material happens due to accretion, raises the temperature at the base, which is the degenerate part on the white dwarf, and ignites a thermonuclear hydrogen-rich material, leading to what we call thermonuclear runaway. And that is what leads to that massive eruption that you see. Okay? The critical mass which is needed is lower if the mass of the white dwarf is higher, and because it has a higher surface gravity. And then novae are expected to occur on the white dwarfs that are near the Chandrasekhar mass limit and increasing to a high rate. This is another attractive part because they are the progenitors of type 1 supernovae, which are our distance ladder scheme. So the energy which is produced goes from hydrogen to helium through this cycle of carbon-nitrogen cycle or oxygen-neon-magnesium, and it comes out as a gamma ray burst. So Fermi is actually detecting these things quickly and very fast, even although optical people were there, but now Fermi is catching them very fast. And that couples with the surface material, which is then ejected, and that what leads to blast. That is the whole radiation pressure that's creating this huge shell. So these ejected shells have pretty high masses, and they're very high speeds. So there is a lot of high resolution spectroscopy coming into this play in this case. This ejected shell is optically thick to high energy radiation, and that is why you see most of the time first as optical brightening. Because if you don't have a Fermi or a gamma ray detector, then you see it in, first in optical and UV. And this, complex radiation transport processes take place, and then the physics gets quite complicated. So the ejecta are not in hydrostatic equilibrium at that state, and the photospheric radius is shrinking with time as the density of the outer ejecta decreases with continuing expansion. And this allows then the X-rays UV to start coming out. Okay, so, and then you can study, so they are truly multi-wavelength objects in some sense. This is bright in optical during the early evolutionary phases, declines in optical, and becomes brighter in UV and X-ray, and lasts there for days to weeks. With this continued outflow, the density of the outer ejecta goes down, and then it becomes transparent. Eventually, the photospheric radius will shrink to near the surface of the white dwarf, and the observable spectrum then peaks in the soft X-ray. And that is what we call super soft phase. And that's where SXT comes in prominently in this studies and so on. And that's another reason I chose this example. So most of the soft X-rays are first absorbed in the interstellar medium with typical values and with the hydrogen column densities in those directions. The spectrum then is observed, what we call super soft source criteria, which lasts for a few days. So we have, over this time, due to target of opportunities and other planned observations, we have covered quite a few of novae. The most recent one was the one that occurred in 2021, and we were able to catch it very well. And then you have the Andromeda. Andromeda is a face-on galaxy, is a factory for observing such novae. And for some reason, it has a lot of such novae seen. And if you really want to discover, you keep looking at M31, Andromeda, and you will find that. That's a lot of people do that. So this is the example I'm giving you from the UV snapshots where they put together a lot of observations. And this details you'll probably see in a poster by Jadojit Basu of IIA, the collaborator. And now this is 42 known novae were actually observed in FUV, 15 of which have been detected in multiple filters, and going down to 23 magnitude, okay, for a 3 sigma detection in a broadband filter, which is, I think, the F148, which is the nanometer wavelength, and in multiple epochs. And they put together this image, and you see the central part where you have novae which are in yellow stars are in outburst, and then you could identify with looking at older images which are in pre-outburst and which are going to be in post-outburst. And so also you see the colors and so on. So, and this is the example of one famous nova which occurs every year. And that we have been observing for many, many years with AstroSat. And you see it is right there in the middle there of one of the exposures with AstroSat. And it is not exactly predictable. Every November, we did observe it in November 25 also. And this is, within a week or 2 weeks, it is almost decided that it will happen and so on. And you see this is the indication. Though AstroSat started observing in 19 and has continued to observe and so on. And it's a very weak object, even when it happens in the, it's in the outburst and so on. In SXTs is very difficult because again, the point spread function of SXT not being so great, because of the non-rigidity of mirrors and so on. You have this in the center. It is seen in the center there, the weak source, and the way you identify is to look at the radial profile, and there is a source there, and there is an unrelated source on the side which is much brighter, and you can actually take it out. The other advantage of AstroSat, other satellites are doing snapshots. They are taking half an hour at the most, and they can't spend most of the time, including Swift, and so on. So we have, we need long time. It actually sets the sensitivity of SXT also, because this is the faintest source that you see 0.01 counts per second, well resolved in the center with the exposure time of, which is like 1 week of observation, continuous observation, okay? And you can see the spectrum, how it evolved. We combined with the Swift and so on. XRT is on the Swift, SXT is on AstroSat. And we have a wonderful comparison. And the idea is, since this eruption lasts only for a week at the most, and you have to be then catch during that week and see the super soft phase. We can get the spectrum, and you see the comparison of Swift spectrum and SXT spectrum in those two graphs, and it's a wonderful thing to study. So these UV and soft X-ray fluxes are found to be anti-correlated at the peak of the super soft phase, which has not been reported before. This was one of the first new results. This implies that both originate on the surface of the white dwarf and could arise during the reformation of partially disrupted accretion disk. And the other thing that we were able to see was this recurrent nova in Large Magellanic Cloud, another weak source. And unfortunately, our target of opportunity looked at the yellow symbols there, and which happened to be the minimum seen with the Swift and so on. But we could see a dynamic variation on the spectrum. And so see you have the energy on the horizontal scale, and you have the days on the vertical, and you have the count rate on the top. And you see that orbit by orbit of the AstroSat satellite, the entire flux, the spectrum is evolving, okay? And you don't understand that fully, the reason for that, okay? So, and these are the kind of interesting things you can do by trying to study these variations. So you see a blue thing, which is the super soft phase, appeared and disappeared, and then appeared again, okay? So these are some kind of activity on the surface of the heating, and the process of accretion, doing this variety of things and so on. And I picked one of the spectra and compared with the different epoch and with the XRT taken on the same day, same time, and so on. This recurrent nova, which happens a few years, again you will see more results with Judhajit Basu's work here, and you have persistent UV plateau and its temperature, and we studied with UV and SXT. So you can see probably one of the few examples that we have UV as SXT, as Professor Agarwal was asking. You can see the UV magnitude versus the SXT count rate, and you see the evolution, and compare these two, and you find that this is possible only if the accretion disk is not completely disrupted during the blast. So there is some persistent disk still remaining even though the blast has happened. There are other fascinating objects. It's called symbiotic recurrent nova. There are only 10 known in our galaxy, and 10 are the total recurrent nova known in our galaxy. Only 4 are symbiotic. And symbiotic means you have a giant and your dwarf. As you saw in the previous talk, they live in very different parts of the main sequence, and they come together, and we call them symbiotic relationship, And so you have this one happening in 2019, V3890 in Sagittarius, and I was able to convince AstroSat to point at the observatory for that 2 times, and we got some wonderful new results. These are the only 4 known of this type, and so on. And you see the evolution. And the main thing was, we were the first to discover when the super soft phase happens, when the whole system becomes transparent to X-ray radiation. And that is that blue patch you see on the left. And that happens 9 days after the blast. And the blast, this phase lasted only for 20 days. So, and we caught it again. Chandra observed it before it happened. We observed it during it happened. Swift took some snapshots and XM. So here, a lot of people came together, and we put together the paper from using various observatories and so on. And most recently, this 2021 NOVA, which is a new system, and this is the fastest NOVA known today. The whole thing lasted only 4 days. And so it was on June 12, 2021, reached a maximum on June 12.96 and so on. So those are the records, historical records. And you see how Swift took snapshots in the crosses, and we took very long looks at those 4 colored dots and so on. And you find some extremely interesting result, even though New Star, Chandra, NICER, everybody was trying to look at that. And we had wonderful data both in the UVIT. In this case, we even have the UVIT grating spectra. And we looked at the UV grating spectra is being used mostly by the CV people and the Asian people. My friends in Asian, Gulab will talked about that. And so this is how it is varying. You see AstroSat, you see the variation, and if you pick up even a short part of it, so you see the comparison with NICER and Chandra, and the SXT is the blue, and then you start comparing, each pulse is different, okay? So this has, we found that it has a 500-second period, and this is amazing thing that even within each dot, you can pick up these variations which you don't understand, okay? And in UVIT, you have the filter data in various filters, and it's a continuous decline, okay? Whereas we had increase and then decrease again, whereas UVIT showed a continuous decline throughout. And there was no periodicity observed. This is the period. Each period is different. So on 37-day, 38-day, 54-day, and the NICER comparison matched perfectly with us on 37-day, and so on. So you had this was very satisfying. You have a NICER at the same time, we had 60, and you can match them perfectly, and so on. But these variations on the pulses is extremely, problematic even now. These are the spectra which took with S60, and you can see it's extremely soft, nothing beyond 2 kV. And that is somehow disadvantage that you have UV at S60, but unfortunately you can't get any detection in the lax PC and such systems. But when you go to regular MCVs, lax PC also comes into play. So, and here we found many absorption edges and so on, which told us what kind of white dwarf it is, and oxygen, neon, magnesium white dwarf seems to be much more likely, and so on. And then you have the variations from different phases, and you see the change in the black body temperature and luminosity. And this is the UV grating spectra, okay? And on all those 4 observation days, we have the grating spectra taken, and you saw how the lines strengths are varying as we go, from silicon, nitrogen, and oxygen, and for different epochs and so on. But there is no periodicity as seen in X-ray, and it's a continuous decline. Okay, this is now a regular magnetic CV. Okay, and you have, this is work done by one of my master's thesis students. She's here and she'll be presenting more details on that. We combined it with various Gaia and other observations and so on, and even including salt data, which Buckley is here, and he collaborated with us. And so we tried to put together as many observatory satellites when we are doing with AstroSat. So there's a long-standing understanding with David that whenever we observe with AstroSat, he will put his salt or any of his other spectrographs which are available on South Africa and so on. And this wonderful experience. So we have a weak X-ray source, and we could do the periods from XMM Newton, AstroSat, and combined XMM and SXT and so on, and discover various periods, etc. And this is the from SALT, the variations, etc. And the evolution of the spectra in UV. And finally, the conclusion was that this is more like a ring-like accretion system, okay, and which is a rare one. And this was a model proposed by Norton et al. That we found that all the periodicities and all the ratios of the spin frequency of the white dwarf compared to the orbital period of the white dwarf and this main sequence star matches with the system, which is more like a ring-like system and so on. So high asynchronicity. So these are some kind of intermediate systems which are evolving from intermediate polar to become polars and so on, and get synchronized. And these are also very rare. There are only 3 or 4 such known systems. These are called, EX Hydra type systems and so on. This is a new, which we are still studying, and this is again a big collaboration. And this is a integral discovered CV, another low field polar. So we're looking at extreme systems, not looking at the regular CVs and so on. Okay? And so you have AstroSat, XMM Newton, RXT, SAO, all being put together. And this is the grating spectrum of another CV, which is the TX Col, Columbi, Col for Columbi constellation. And again observed with AstroSat, but is still not fully analyzed. We have done the various periods. So many periods are in there in the system. And you know, there are orbital period, disk precession. And so you have multiple handles on this system, and it probably gets too complex when you're too close and too near, you see too much detail and so on. And we tried to put together the UV spectrum, S60 spectrum, and lag species spectrum. This is probably one of the first only CVs that have the data in all three bands and using the full multi-wavelength capability. I've been a great proponent of the multi-wavelength part of the thing, even though they were difficult to you know, put together. But here we have all three. Okay, and so this is the IP, intermediate polar, which means it doesn't have a very high magnetic field, is not fully synchronous, and it has a long period and so on. I think that's about it here. And this is my whole list of collaborators because these campaigns require handling these beasts from as many angles as possible, and you know. So you can see South Africa, even Swift Data, Kim Page, Beardmore, ESA, XMM, Jan Ness, he's in the ISRO headquarters, Oreo, Jeremy Drake, Eric Schlegel, Luna, you know, of course, Paul Barrett, who used to be worked with me and David many at different times and so on. So I think it's been fun to observe because for grating, Gulab is the person who has made the software and everything available for the using of grating for AGNs. I'm using for CVs with his help and so on. So it's been a wonderful thing to go through these systems which are less studied and not very, you know, popular among the people.
Thank you very much. So, open for questions.
What is that?
There's a near UV, right? Data of 2016, not analyzed, I couldn't understand that.
Firstly, the grating,
Eh?
see the grating analysis became available in 2021, okay? And after that I have had people to put together, okay? Grating analysis was developed by Gulab during COVID times.
Not before.
Not before. And nobody else developed it.
Yeah, Professor Singh, in the beginning of your presentation, you emphasized the nova phenomena, where you basically emphasized that during the explosion, it is the UV and the X-ray, which would contain lots of information. And with the AstroSat, you know that it has been very difficult to observe the galactic plane where most of the transient should happen.
So we pick sources a little away.
Right, okay. That's right. So my question is, so do you envisage the need of a dedicated X-ray UV mission, particularly for this purpose, for the novae in particular and transients in general? This is also in response to what Professor Dipankar Bhattacharya has mentioned, that now we should be looking for a very specific topics when you are planning the next mission. So how do you think of
for wide dwarf studies, whether they are isolated or whether they are in binaries, UV X-ray will be perfect mission to focus on, soft X-ray and UV.
Yeah, thank you.
Any other question? There.
That happens. That is typically seen by Fermi-LAT, I assume. Does it have a lower energy tail that CZTI can catch, like several hundred keVs?
Actually, we don't know. Nobody has seen it yet. Okay, so the MEV results are not there. GeV results come from the Fermi, and there's heat immediate. So now actually there's a tussle between who got the nova first. Fermi got it or the optical guys got it. Okay, but if the Fermi detects it, it will always give you a little earlier than the optical.
I think we should dig into that. CZTI should be able to see it.
Yes, it should be.
I think
Given recurring nova.
But the thing is, you don't know the direction. You don't know where it's happening.
Post-fact.
Post-fact.
Thank you.
I think we are running out of time. Thank you very much, KP, for this wonderful talk.
Okay, first of all, I would like to thank the organizer for inviting me, and I'm very honored to be part of this celebration. It's amazing. Thanks to the organizer. It's a very nice event. So going forward with accretion, I would like to focus on accreting millisecond X-ray pulsars, so neutron stars that are accreting matters. And I will try to show you how AstroSat help us and will help us in the future to try to understand better those systems. Let me try to set the scene, and then I'll show you 3 case studies where AstroSat actually made significant contribution. Let's focus on low mass X-ray binaries. We have neutron stars that are accreting matter from a low mass, like solar-like mass, via accretion disk. I don't see the pointer. Okay, here. Binding energy is converted into heat, and we will see later, we have several regions where actually X-rays are generated. One of these regions is actually the surface of the neutron star. The neutron star being such an extreme environment is actually quite interesting in terms of how X-rays will come out from this surface. What can we summarize for neutron stars? Basically, we have something of the order of 1.4 solar masses, let's say, that is compact in a sphere of 10 kilometers. Density at the center is extreme, and magnetic field can be anywhere between 10 to the 7, 10 to the 15 Gauss. Well, numbers are covered there. On top of that, those systems are spinning in a range that can be of the order of 100 seconds up to milliseconds, and I will focus on the milliseconds. Basically, this is a cartoon that summarizes what we seems to know about those systems, and we seems to know quite well up to this region here. We don't see the pointer. What is called the inner core, where the density is so extreme that there is no way we can replicate that in laboratory. So there is some uncertainty of which kind of material is actually there. And this is bread for theoreticians that actually, by means of equation of state, will just try to, populate the inner center of this neutron star, giving some different prescription, and they will come up with some prescription for mass and radius. I'm not going to use this plot, which is quite complex, to tell you that we will constrain equation of state, but each of these mass and radius relation means different compactness and different relativistic effects that we expect from the system. And therefore, pulse profile emission from the surface will be significantly affected by that. By setting the scene, I'll introduce accreting millisecond X-ray pulsar. A movie should start. As you will see, their matter is following from the companion star through the accretion disk, and when things zoom in, you will see that at some point magnetic field from the neutron star will just stop matter, channel some of them in the magnetic lines, and matter can accrete on the poles. If that's the case, those regions are much hotter, and because of lighthouse effects, this system is basically what is called a pulsar. One thing that you can notice is that once matter is accreting, it's actually accreting angular momentum. So we should be able to see this system accelerating in real time. And that's something that we'll see actually sometimes. Now that we have introduced the subject of this presentation, let's see how this peculiar system relates to the neutron stars that we know. Actually, this is a list of known accreting millisecond pulsars. There are only 24 among hundreds of neutron stars that we know. So the population is relatively tiny, but they have something very peculiar. If you compare the spin distribution, which is the blue one in this graph, in this histogram there, with the population of so-called recycled millisecond pulsars, you will see that they share the same spin interval, which means that there must be some evolutionary link between these two populations. And that's exactly what led to what is called the recycling scenario. The idea is that the radio millisecond pulsar that we see are actually systems that has been accelerated during a long-lived phase of accretion. And accreting millisecond pulsar are basically a stage of this long-lived accretion phase. So basically, every time we see an accreting millisecond pulsar, we are seeing a radio pulsar that is accelerating, rejuvenating, let's say. The idea is that when the neutron stars are born, they populate this region here. This is how quick spin is changing with time as a function of the spin period. So they are usually born here, relatively fast, spinning, but then they lose energy because of rotation. And once they lose energy, they go down towards this line, and at some point they're not observed anymore. They go in what is called the pulsar graveyard. If they are lucky enough to be part of a binary system, they can actually accrete matter, accumulate angular momentum, and this slow rotating, let's say, old pulsar that can actually start accelerating again, and they end up in this region, low magnetic field, fast spin. In 2013, we had for the first time the bulletproof that sealed this theory. We discovered a system that actually, while accreting, behaves as an X-ray pulsar, while when accretion stops, it behaves like a radio pulsar. So basically, we have linked the two populations. Where do X-rays are generated? Basically, we expect soft components from the neutron star surface and the disk, and hard component due to the interaction of soft photons scattered by a cloud of hot electron. And this is actually where AstroSat can be very useful, because it has the possibility to cover the broadband with the two main instruments. One other interesting part is what is called a reflection spectrum. Hard X-ray photons interacting with the disk actually create a reflection spectrum that is characterized by features some like iron emission line, absorption, and Compton amp. They're actually coming very close to the neutron star, and they are shaped by gravitational redshift, light bending, and so on and so forth. So if we manage to study this part, we can actually get information on where the disk is truncated and how the neutron star is actually behaves. Why do we see so few accreting millisecond pulsar? One of the possibilities is that the interaction between magnetic field and mass that is accreting sets where the disk is truncated. It can be that actually when you are creating much more mass, so luminosity is high, you are screening part of the magnetic field, and because of Rayleigh-Taylor instabilities, matter can penetrate in the equator, and you don't have any more poles that are brighter, so you don't have the pulsar effect anymore. On top of that, those systems are very variable. They stay in outbar, so they accrete matter generating X-rays only for a few days up to months, and then they stay quiet for long phases that can be decades for some of those systems. So it's quite difficult to catch them, but when you catch them, for example, with AstroSat, you need to extract as much as possible information, and that's one of the key features that made AstroSat very useful for these sources. Here I try to summarize why AstroSat is useful for studying accreting millisecond pulsar. I don't know if you see the bottom sentences there, but basically the possibility to cover software spectra because of XXT and LuxPC allows you basically to disentangle and to be sure that you, for example, can catch reflection spectrum. And also the possibility with the high timing resolution to check pulsations regions where actually the hotspots are not contributing that much. It's telling you about the geometry and how pulses are actually generated. The tools that we use usually to identify and to study those systems are summarized here. The first one is what is called pulse profile studies, let's say. So we take the full band, we make a pulse profile, and we try to understand how complex is the pulse profile. Then we have the possibility, for example, to study how the pulsation are changing as a function of energy, and this is telling us what are the different contributions on the system. And the last one is actually the possibility to construct the broadband spectrum. Let's see how those things can be applied to real systems. The first one is, let's say, the prototype of the accretive millisecond pulsar. It's the first one discovered in 1998. It goes in outbursts basically every 2.5 years. And AstroSat had the possibility to observe it at least twice, 2019 and 2022 outbursts. Among all the things that you can do, that AstroSat did for these two outbursts, I picked the composition of the pulse profile. As you can see here, basically we are collecting all the photons in the 3 to 20 kV, in the 3 to 30 kV energy band. And because of the high statistics, you can see that the pulse profile, the one in red, is actually quite complex, quite far from the expected sinusoidal profile that is usually imagined for a neutron star with a standard dipolar magnetic field. And as you can see here, both in 2019 and 22, the high energy pulse profile is quite complex, up to at least 3 components to describe the profile. Why is this important? Well, it's quite important because basically we are mapping an energy range which is relatively far from what we expect from the poles. We expect the poles to be described by a black body of temperature of the order of 1 kV. Here we have emission that is going up to 20 to 30 kV. So there must be something else that is playing a role in shaping the pulse profile. On top of that, we can actually do something more refined in terms of the analysis. So basically, we take the full energy band and we try to reduce in intervals in energy and try to see if the pulse profile is significant. One thing that you can see here is that you lose the amount of the complexity of the profile because of the statistics, but you end up seeing that at least 2 components are always there, even if you take small energy bands. And you see there is a trend. The amount of photons that are pulsating actually seems to decrease for this source as the energy goes down. That's for the fundamental component. On the other end, for the first harmonic, seems to do the other way around. And that's peculiar because it's telling you basically that you have 2 hotspots that are actually contributing in a slightly different way. Although this is not, so we have diverse behavior for different objects among accretive millisecond pulsar. Being able to do this kind of study for each of these sources is giving us more flavor in terms of what is going on the geometry, on the distribution of hotspot and how they are contributing in these sources. The second case that I highlighted is another accretive millisecond pulsar. I focus on the spectral analysis, although all the timing has been done also for this one. But it was quite peculiar the fact that AstroSat got the source in one state that is not usually observed for this system. This is called the R state, meaning that emission from the corona, so these electrons surrounding the neutron star, are actually dominated. why is this important? If you see black and red, SXT and LUX-PC are basically covering very large energy spectrum in such a way that we are sure that the continuum is such that the reflection component is a significant component that needs to be added to fully describe the energy spectrum. So basically, by doing that, we are ensuring what is the ionization state of the disk, and therefore we are understanding what's going on close to the neutron star. The last case that I would like to show you is, again, another accretive millisecond pulsar. This is from a 2018 outburst. And in this specific case, what I would like to show you is that having a full and broad energy range covered by the LUX-PC allowed us actually to see how the pulse profile evolves with energy. This specific case, the 3 to 20 kV, are basically showing a pulse profile that is stable. It's not changing. If you pay attention here, basically you see that the peak is always around 0.25 in terms of phase. And one thing that we notice is that the modulation, so the amount of photons that are actually pulsating at the spin period, seems to decrease as the energy increases. And this doesn't seem to be a problem of statistics. So it's not you have few photons at high energy and therefore you don't detect the pulsation. It really seems like the mechanism, wherever it is generating high energy photons, is not pulsating at the same spin frequency. So there must be some sort of interaction that is making the system lose coherence. So pulsation is losing coherence at high energies. This source is very peculiar, and I don't want to spoil, but yeah, sorry by the fact that half of the sentence is covered by the timer. But this source has been the only one that show a very peculiar type 1 burst, and AstroSat was the only one to observe this type 1 burst, and you will see more and get more detail on Sadip's talk on Saturday. But I suggest you to watch that seminar, because basically this double profile of the type 1 burst seems to be something unique and can be explained with interesting physics there. I try to put in bullets what could be the future contribution of AstroSat in terms of better understanding accretion millisecond pulsars. And the 3 points that I highlighted is the possibility to get more information about pulsation and accretion geometry. And the key here is just to trigger wherever transient that looks like an accretive millisecond pulsar with AstroSat, because he clearly has the capabilities to give us meaningful information. The evolution and recycling, the more system we get, the more we have chances probably to link accretive millisecond pulsar with other millisecond pulsars. And the other part is that, I don't know if you realize that, but when I show the histogram with all the spins, you probably realize that there was a shortcut at around 720 Hertz, which is the maximum spin that we observe in a neutron star. There is no physical limit that stops those systems to rotate at a value higher than that. So it might be that actually we just need to look more and to get lucky and get faster systems. So yeah, I'll stop here. Thanks for listening, and I get questions if you have.
Thank you very much for such a nice, wonderful talk. Open for discussion, questions. Sachi.
Thanks, Andrea, for the nice talk. So I have one question. During X-ray outburst,
Yes.
in the decay phase also, you
The
do,
what, sorry?
in the decay phase of the outburst,
Yes.
you do see thermonuclear burst from the neutron star.
You see what? Sorry.
We do see thermonuclear burst from the neutron stars,
Yes.
right? So this outburst should not allow matter to deposit on the neutron star, and because of which it should undergo thermonuclear burst. But how does it happen?
Yeah, well, that is difficult to say because we actually have systems where during the decay, so very low fluxes, actually they still show pulsations.
That's
So-
fine. But thermonuclear burst at the decay phase of the outburst.
Well, sure, but if you manage to, you can imagine also the possibility to build up a layer of material. You need a bit more time to
Maybe.
ignite,
Okay,
right?
One more question.
Yeah.
In the SXT and lag species spectrum, you said reflection is detected.
What's it?
Reflection
Yes.
component. However, iron line was not seen either in lag species or SXT.
The airline there was actually, there was also XMM.
Yeah.
And well, if you check the sensitivity in terms of effective area, XMM probably there is slightly more sensitive. So
Okay.
there must be a problem with statistics. Yeah.
Next question. Yeah.
Andrea, I just want to ask about the sort of transitional millisecond pulsars and why you think they're even rarer, right, than the accreting ones. And what's the fundamental reason for the fact that in those systems they go from an accretion to a propeller state, whereas most of them don't?
Yeah, there is a very good question. One thing, for example, that is missing from accreting millisecond pulsar is radio counterparts, right? Every time they go in quiescence, we don't detect them in radio. There are several theories, one of which, for example, is the possibility that when they go in the radio state, they actually switch to be a radio pulsar, but then they tend to, for example, interact with material at the Lagrangian point, material that is not stopping. It cannot, in terms of time scales, it cannot be that you stop completely mass from transfer from the companion star. So in principle, if you interact, so the radiation pressure, the radio the pressure in the Lagrangian point can probably stop accretion there, engulf the system with some sort of shell of material, and that's one possibility of screening radio. That there is one of the possibilities, but yeah, it's a very open question there.
So one last question.
It's also possible that matter has entered inside the light cylinder, in which case it won't function as a radio pulsar.
Yeah, that is also a possibility. And also there, probably you should have matter that is ejected from the system, right?
Okay, thank you very much.
Yeah.
Now we are running out of time.
All right. So in the SOC, we were discussing about different topics together, and then we found that one particular topic called black hole X-ray binaries, we have a significantly large number of papers. I mean, like something in the order of 60, 70 papers. And so there was decided that there'll be 2 invited talks or something so we can review them all in the whole thing. Now, and unfortunately, they picked up me and Santabata to talk, unfortunately. So, but fortunately, I made a deal. I made a very good deal. The very good deal was Santabata was going to talk about, sorry, oops,
for a review of the AstroSat science results from black hole X-ray binaries, you can listen to Santabro's talk. So all those papers, those 100 papers, Santabro is going to read and talk about them. So I don't have to do that. And so then I have to decide what I should do. So what I will do is, I'll ask the other question is, why there were so many papers on and results on black hole X-ray binaries. So while I'm going to talk about the abilities of AstroSat to do unique science and X-ray black hole X-ray binaries, and although my talk will be limited to the science done by black hole X-ray binaries, I think it's quite generic and it actually applies to all X-ray binaries, and that's the reason why we are doing that. So you will not find any science results here except for one, and I'll come to that right now. The first and important one which started off for our black hole X-ray binaries is the ability to detect polarization, and this is by the CZTI, and this was absolutely unique. We could not do anything, and this is the only result which I will write down, that for a black hole system Cygnus X1, the polarization was detected at in the 100 to 400 kV band, a completely unique activity and all. The reason why we could do this is particularly the CZTI design and that of high timing resolution of 20 microseconds, so you could know that there was a Compton event in the whole thing. And it's a wonderful experience where something which should be a nuisance is something which should have been a really terrible thing, Compton events going around in your detectors, has been turned around into one of our best results which we have got from AstroSat 1. So that is one of course, AstroSat's great legacy in physics. But the main reason why we had so many works and publication is the rapid timing ability of especially LAX-PC instrument. And LAX-PC has a large effective area of, I write down 6,000 to 2,000 for a particular reason, that we started off with 6,000 with 3 detectors, and now we are left with 1, so we have come down to 2,000. And so that is the, but it's a 6,000 to 2,000 still a large, and I'll come back to that. It's a large effective area at energies greater around 30 kV, which was unique. The earlier satellites which were done with RXT was also in the same ballpark, but they were not that effective area on 30 kV. Now this is extremely crucial for people who don't do rapid timing. I want to explain that the signal to noise of rapid timing analysis goes proportional to the area of the detector, not as the square root of the detector. So if you have something which is from 6,000 to 2,000, it is 3 times better. I mean, the signal noise is 3 times better. It's like for most optical astronomers, that will be like going with the diameter of the optical telescope. So that was important, but there is a catch. There's always a catch, and the catch is background. Now, the signal to noise of timing, I'm just talking about timing information, goes like source plus background square. So again, if a source is dominated by background, this is source by background, where's the light? Okay. Yeah. The source plus background here, oops, this is tough. Now, this 1 over the background square means that if your background is not well controlled, your signal noise will really go down, and a lot of science you cannot do. This is the only figure I'll be showing where in the bottom part you can see the background light curves of LAX-PC 10 and 20, and on top of it is the actual background subtracted spectrum of Cygnus X1, which is one of the brightest sources we can see from there. And we can see that around 30-40 kV, the background is comparable to the source spec. And the point which I want to make here is that LAX-PC background is pretty good, it's relatively low. And I really would be thankful, because if the instrument had a background, let's say just a factor of 2 more, the signal noise would have gone down by a factor of 4 on these things. And a lot of this wonderful science which you're seeing would not have been possible there. On top of it, LAX-PC background was also well modeled with a systematic error of about 3%. Yeah. So I'll continue with the background thing. The LAX-PC is important because the VTOS worked properly. If there was something wrong with that, we would have been off by easily by a factor of 2 and 3, and that would have destroyed much of the science which is coming out. So that's the good point. However, as I said coming out, if this was the only thing which LAX-PC AstroSat could be doing, I would have considered incremental improvement. In the sense that we had RXT, which was doing has measured things, and we have got LaxPC now, which can do things slightly better, not at a magnitude level, but good control. We would have been looking at sources and confirmed a lot of what RXT had done, and also improved it because LaxPC was much better in the high energies. But even then, it would have been just one incremental factor. There was one very important factor in AstroSat which has made it completely unique, and that is that we had SXT on board at the same time as LaxPC. Now that gave us the advantage that we had soft energy spectrum and hard X-ray spectrum at the same time as we have rapid timing information. This was completely unique. Even up till now, we don't have a single instrument which can do that. There's never been any instrument which can ever give us, yeah. So I was saying, up till now we have, let me go back first to the other factors, sorry, I missed that. Other factors which are important for the rapid timing behavior. One is the time resolution. Of course, the time resolution was at 10 microseconds now. I just want to clarify that in many people have heard that is the most important thing of LaxPC. That was not. The most important thing of LaxPC was a large area and a low background, which allowed it for timing. Which even if the resolution was a few times factor more, we wouldn't have been that bad off. Its energy resolution of 15% was amazing. It was very good. That is why we could do high timing resolution in different energy bands. Even if we were better than a few resolution more, it wouldn't have mattered much, as Andrea was saying, that once you go down to low energies, your statistics goes down. So that would not have been good. The dead time of 40 microseconds also was good. It was about the kind of values which we could handle. For example, if the dead time was a few factors higher, we could have lived with it, but we would have struggled with the modeling of it. I know I had to struggle with the modeling of 40 microseconds, but if you do it, if it was a little higher, it would have been a little bit more difficult to do that. But as I was saying, the real advantage of AstroSat was the broadband X-ray spectroscopy, and I cannot but re-emphasize on it more. It is one of the unique, and this allowed for finding correlations between spectral parameters and timing parameters. Now, just for people who don't get this, it is like, you're seeing an object, it has a temperature, it has an object. Now, it is varying. Now, I want to know what is varying. Is the temperature of the system varying, the optical depth varying, is it the size varying? You can't get those information if you're just looking at a small energy band out there. You needed a full energy band to get the information, and that's exactly what has happened in AstroSat. And that, because of this kind of idea that we could look at the whole energy band of things, we could measure things like the accretion rate of the system, the inner disk radius, at the same time measuring the timing property, which allowed us to measure fundamental theories of things. How could we do broadband spectroscopy? It was not just enough to have a two instrument like SXT and LaxPC on. It was important that the spectral error on the spectral calibration was constant to be less than 3%. And I think that was very critical. If it was much higher, we would have been in trouble. The second one is a slightly controversial statement, but I think it's probably true, that for X-ray binaries are so bright that they cannot be reliably offered by many of the amazing satellites which you had before, like Chandra, XM Newton, and even by Swift XRT. The critical thing was that SXT spectra was not piled up to 40 counts per second. Now that was a big advantage, because that allowed us to see the brightest sources without problem. In fact, there are some sources which go even brighter than 40, like a lot of sources go above 40 counts per second. But then what you can do is you can remove the annular part, the circular part of the image of the SXT, and that removes the pile-up condition. Just for when a pile-up is when two photons hit at the same time. So whenever you have at the same chip, so that causes a lot of problems in the holding. But essentially, if you get that idea, is that SXT was one of the first instruments which could reliably see bright X-ray sources in the software, and that, along with thing, allowed us to do the broadband spectral analysis. Absolutely. There was, in fact, this is one of my last slides. I'm going to stop quite quickly out here, even without break. The next important thing which happened, which allowed us to do lots and lots more science, is that AstroSat was flying at a time when, is flying at a time when there was ample opportunity from other observatories. There were many other observatories which are going on at the same time as AstroSat is, or were, because now NISA is no longer there. But this gave us an opportunity to have a synergy between AstroSat science and others. I'll give two examples of that, and both of them I think were critical for doing black hole X-ray binaries. The first was synergy with this instrument called NISR. The NISR is a very large area detector, but it's in a soft X-ray band. So it does exactly what LAX-PC can do, but in a soft X-ray band. So for the very first time in our history of doing science, we had unprecedented, from 1 kV or 0.7 kV to 50 kV, we had rapid timing information, which was not there before. So we could just talk about how the energy, how the variability occurred in different energy bands over large amount. That was very critical for doing things. And some of the best results have come out when we have combined NISR and AstroSat together in the whole thing. The other one instrument which is very useful for us was NuStar, because NuStar is a high energy one but has much better spectral resolution than LAX-PC. So when you combine that NuStar with AstroSat, what you get is you get excellent spectrum all the way from there, and you have the timing information from LAX-PC, and that was what caused the way. So I've been saying that everything has been fantastic and very good, but there should be, of course, certain lessons learned or certain expectations, wish list, that what we could be doing more. So I would like to first emphasize that possible improvements. Now, there's always a large wish list of people from different communities, and I've just chosen 2 or 3 possible things which I think were important, which I would think would be my wish list. And I'll come to her. The first one is to reduce the spectral response calibrity from 3% to less than 1%. If that had happened, our science would have really increased substantially. And mind you, I think there's another reason why this 3% to 1% did not happen. And that is, I think, one of our bigger failures, was that there was a certain disconnect between the community users of AstroSat and the people who are doing, and the role of calibration. I keep telling people that calibration is everybody's business, is everybody's concern. So if more people in the community are willing to go into and trying to do the calibration better, we could have gone from 3% to 1%. So in other words, we should not be relying only on the pure instrumentation team which was built at AstroSat 15 years ago to do the calibration. It should be done in the world. We also had, I think, that we missed out a lot of opportunity having more coordinated observations with other satellites between AstroSat and this. This was slightly more in thing that we didn't have any actual policy making of having joint ventures, like XM Newton and Chandra have their own policies where they can actually collaborate on having simultaneous observations. So many of the AstroSat and other observations were done serendipitously. That was just luck, that they happened to be looking at each other at the same time. Very few coordinated observations were taking place as well. I completely missed out UVIT. Nothing about UVIT in this whole thing. And that is because, of course, most of these sources are in a galactic plane. Most of the sources are bright in UV, so they can't be done. But that is really not true. What we could have tried a little bit more is to search and to go for actual some sources which could have been observed by UVIT. For example, this famous black hole source GS-394, after some very complicated 9-pointing systems, we were able to find out that actually it is safe for UVIT and was observed by UVIT, but that's a limited one. So we should be going a little bit more aggressively on doing that. So finally, the summary of my talk is on behalf of the committee, I thank ISRO and instrument team for making AstroSat. It has made our life wonderful and we have produced such great results. Thank you.
Thank you very much. It was very wonderful talk. You summarized the capability for timing.
Yeah, Santapur will do the rest.
Okay. The results will be covered tomorrow. So open for questions. Sure. UAT.
Yes.
UAT has many filters, and one of the filters is very narrow band.
Yes.
Just for information.
I know, Shyam.
Yeah.
We should have gone and studied and looked at everything, how we could have done it. Not optimized.
Anyone else?
Could you please clarify that signal to noise equation, that source divided by source plus background square?
Yeah. So source is there's a confusion always which I get confused with. A source is either can be a total count or you can say net, which is source minus the background. So what I'm seeing by the source here is the actual source without a background. Net, right? Does that clarify?
The equation seems to be like the maximum SNR could be 1 if you go by that equation.
What?
Can you?
No, it's proportional to.
Oh.
It's proportional to.
Okay, maybe I'm.
So when the background is 0, it doesn't matter. When the background is lower than the source, it doesn't matter. The background doesn't matter. It's proportional to.
Any other?
Thank you for the talk. One aspect of XVC which I want to bring to notice of everybody, the XVC is a high time resolution mode.
Yes.
In which you can count photons in 10 microseconds. Okay? And the spectra only 2 broadband. Now that mode is ideal for studying kilohertz QPU.
Yes.
For example, even SCOX one, you don't know what is the QPU is, kilosecond QPU there. Similarly, and so I made a proposal that because the SCOX one is very bright, do it offset pointing.
Yes.
So that you can read. But unfortunately, I think people thought that this would destroy the elections, which is not true. It did not happen from my experience, I can say. So that still leaves door open for study of kilohertz QPU.
Yes.
In dozens of them.
Yes. Thank. I think the statement was that we could have done from a burst mode, and as well as also from an offset thing to look at very bright sources, which we did not do to the full extent. And I would agree with what.
Question there.
Hello. So I am a bit confused about this. You said that if the energy resolution was a bit better, we would have finer bins but lower counts in each of the bins. So the statistics wouldn't exactly work. But couldn't we just use cache statistics for that part? Those,
No,
statistics. Or we could bin them in different situations as well.
No, I think the cache statistics with the chi-square or the cache statistic, that is very useful for doing spectrum.
Yeah.
And for spectrum, we obviously need better spectral resolution.
Yeah.
I was talking about timing.
No, you said for energy resolution.
Energy resolution for timing.
Oh, okay, got it.
Energy resolution for timing. That's a different ball game than energy resolution for spectra.
Got it. Okay, now I understand. Thank you very much.
Hello, sir. This is Ramesh. You have mentioned in a few minutes back, up to 40 counts per second, there is no pile-up, right?
No pile-up, yes.
Pile-up. So what it depends on? It depends on energy, or it depends on a resolution, or it depends on...
No, it depends only on the count rate.
Sorry?
It's only on the count rate.
Count rate, yeah. My question is, what it depends on, like why it's not pile-up? Because when you consider Chandra, it has a lot of pile-up when it's bright sources.
Oh, no, that depends on what is the seeing, the PSF.
Yeah.
The PSF in SXT was larger, so less photons fall on each pixel. So that's why it was spread out, and that's
Thank
why
you.
it's good.
I will go back to the, okay, the question, interesting factor of bringing 3% to 1%, because
Yes.
though it looks similar 3 and 1, but it's enormous.
Yes.
So what is the visualization or time scale it can be done according to you?
But no, there is no time scale required. It requires motivation and will.
Of course you have.
No. Me? No. I make deals.
Okay. But it is feasible. It is feasible.
Okay, the reason why I'm saying so, RXT PCA
took
went
5
from 6% to 3% and then to 0.5%. That 3 to 0.5% took 10 years.
Anyway.
It took 10 years for them, 3 to 0.5 to 2, but they went from 3 to 0.5.
So
we
should
didn't
go
do
there.
that. We didn't do that.
It's
Correct. So we not reached point.
He says we haven't started. Okay. Anyway, thank you very much.
Thanks.
Very good. So last talk of this session, Gulab Devangad. He'll talk about multivariant view of radio quiet galaxies with AstroSat.
So let me thank the organizers for inviting me to give this talk on multi-wavelength view of radio quiet active galaxies with AstroSat. I would also like to thank ISRO, the payload managers and payload teams, operation team, ASSC supports, etc. And of course, a number of my collaborators, including my PhD students, 4 of them listed here. So let's begin. Let me begin the talk. There are, according to some estimate, there are about 2 trillion galaxies in the observable universe. A few % of these galaxies are essentially active, and the activity in galaxies is primarily identified by the presence of a really bright nucleus, very bright centers in the galaxies which can actually outshine. The energy source for these nuclei, or the very bright nuclei, are not really the stars, but something different. What we think is that in fact now we know that almost every galaxy has a supermassive black hole with a mass in the range of, let's say, 10 million to about 10 billion solar masses. And if you look at the size of the galaxy, it's about 10 to 100 kiloparsec. And if you go into the innermost regions, about a few parsec, then what we have is the center is the supermassive black hole, which is accreting the material and forming an accretion disk. And this accretion disk, we'll see, is emitting in the optical and ultraviolet, which is AstroSat is able to observe. But in addition to that, there are this clouds, some kind of clouds, which we call broad line region clouds. There are some broad line region clouds which are responsible for the broad emission lines we observe in the optical and ultraviolet. These accretion disk and the broad line region clouds are all surrounded by something called torus, dusty torus, and therefore, depending on our line of sight, depending on our view, we can have different kinds of regions, and that's the basic scheme for the unification. But most importantly, when we are interested in the innermost region where we have the supermassive black hole and accretion disk, which is essentially the central engine and which is emitting the primary emission from AGNs. So first of all, this accretion disk, which is the direct result of the accretion flow onto the supermassive black hole, that emits in the optical and ultraviolet, which we call this as a big blue bump emission, which is seen here. Then in the X-ray band, we have a broad band X-ray power law, and that is, that is thought to be due to the inverse Compton scattering of optical ultraviolet photons from the accretion disk onto a hot corona, onto the hot corona, which could also be the base of the jet here. Okay, so and then in addition, we have a few other spectral components like the soft X-ray excess emission, which was actually discovered by Professor K.P. Singh. But the exact origin we do not know, but it could be that the innermost accretion disk is modified in some way, and that is giving rise to the soft X-ray excess emission. So the advantage with AstroSat is that AstroSat can cover the emission from the accretion disk in the ultraviolet, and because we have the far ultraviolet coverage, which means we can actually probe the innermost accretion disk very near the supermassive black hole. In addition, we have the soft X-ray telescope, which can probe the soft X-ray excess as well as the power law, and with the LEX-PC, the broadband X-ray power law component, and in to some extent reflection as well. So here is at a glance, the various studies which have been done using AstroSat on the radio-quiet agents. First of all, with the ultraviolet imaging telescope, particularly with the far ultraviolet, we have been able to probe the nature of accretion disk by measuring the intrinsic emission from this accretion disk. We have also been able to study the connection between the UV and X-ray, which is the direct result of the interplay between the accretion disk and hot corona. And this connection we have been able to do both with spectrally, how the different components, the accretion disk components, the hot corona and the soft X-ray regions are actually connected spectrally, as well as temporally, how the variations in the UV and the X-rays, etc., are connected. Then we have also been able to observe extreme variability and transient phenomena from some of these active galactic nuclei. These, the extreme variability and nuclear transients are recently kind of much more recent, and they are becoming very, very important to understand these extreme activity in AGN. There are something called changing look AGNs, which I'll discuss in a little more detail. Then we have also been able to study tidal disruption events and quasi-periodic eruptions using UV or single waveband X-ray instrument. There are other studies, for example, probes of dusty torus by using ultraviolet and infrared spectral energy distributions. We have also been able to probe star formation in the host galaxies of these AGNs, as well as feedback processes in these AGNs. There are also findings of new AGNs utilizing the deep ultraviolet imaging field, ultraviolet imaging telescope observations. I will discuss only the central engines using the UV and X-ray observations with AstroSat. So here is the ultraviolet imaging telescope grating observations of some of these AGNs. We have actually 8 type 1 AGNs which were actually observed, and we produce actually useful data from AstroSat grating. And they, of course, the AGNs are in the centers of galaxies. So that when we look at those things, this emission from the central region actually is contaminated by various things like galactic extinction, intrinsic reddening, the broad and narrow line emission from the broad line region clouds, narrow line region clouds. There can be some absorption lines also. There are various other various things. So in order to infer the intrinsic emission from the accretion disk, one has to account for all of these effects. One has to model all of these effects, which we have done in this case, and finally infer the accretion disk emission. And when we do that and try to measure probe the nature of the accretion disk, what we find that now generally the accretion disks are, the emission from accretion disk are consistent with what is expected from the standard disk model by Sakura and Sanyayo. But in some cases, the accretion disk is truncated in the innermost regions. For example, what we see is at least 2 or 3 AGNs are actually have their inner accretion disk truncated at about 50 to 100 times the gravitational radii. We also utilize, for those AGNs, we also utilize the X-ray observations, particularly the soft X-ray observations. Many of these AGNs were not being able to detect in LEX-PC. But when we use the SXC data and the UVIT grating data, then we can actually fit broadband spectral models for the utilizing the central engine, the model for the central engine. And we find that the UV emission is essentially, all this broadband spectrum is essentially consistent with the emission from the accretion disk, and this emission being compromised by 2 regions. One is the warm corona with a temperature of about 0.5 kV, that is responsible for the soft X-ray excess emission, and the hot corona, which is responsible for the broadband X-ray power law. But what we cannot actually distinguish is different kinds of geometries. What exactly is the geometry in the innermost regions near the supermassive black hole? Whether there is the accretion flow is stratified. For example, there can be an accretion disk, then the warm corona, and then the hot corona. Or the other possibility, there is an accretion disk, probably it can go down to innermost regions, and then somehow this is modified into soft X-ray and hot and X-ray emitting regions. So these kind of geometries we are not able to distinguish with the data we have currently. The other important thing we have probed is the temporal connection between the UV and X-ray. Why it is important? Because the ultraviolet photons, the optical ultraviolet photons from the accretion disk are being compromised by the hot corona, which means if this is true, then the UV photons should be leading the X-rays, while the X-rays produced in the hot corona here can illuminate the accretion disk and get reprocessed into the ultraviolet emission. So therefore, in such a case, the ultraviolet emission should be delayed compared to the X-ray emission. And this accretion disk, according to the standard disk model, has a temperature profile. So therefore, the radiation at different wavelengths will be arising at the different parts of the disk. So by studying the time lag as a function of wavelength, one can actually probe the accretion disk models, and that is what we have been able to do. This is one example of the light curves in this X-ray, soft X-ray measured with soft X-ray telescope, and then the ultraviolet, then the ultraviolet light curves measured with the far UV channel and the near UV channel. And when we look at, when we cross-correlate these light curves, what we find is generally the UV band or the UV vision is lagging behind X-rays. And that is a proof of the reprocessing of X-rays onto the accretion disk. And these lags, when you look at into the function of wavelength, it turns out that they essentially tell us that the accretion disks are probably larger. The real accretion disks are probably larger than the standard, than what is predicted by the standard Sakura scenario disk. But now with models where we can have an accretion disk and the hot corona something like 50 or 100 Schwarzschild radius vertically up, then that kind of thing can also explain what we observe. Here are the summary of the observations. We have been able to measure these time lags in 5 of these agents, except only in this case of NGC 7469, which actually shows the UV emission leading the X-rays opposite to other objects. So we think in this case the reprocessing is not important, but variability is intrinsic to the disk, and that is the intrinsic UV emission is compromising, and then the delays measured are actually consistent with the compromisation scenario. Now I'll come back, go to the extreme variability events or transient activity in galactic nuclei. There is some interesting class of agents now known as changing look agents. What happens in these agents? They actually, their flux or their luminosity changes by a factor of 10 in 6 months or years or a couple of years time scale. And when you look at the spectrum of these objects in the low flux state and high flux state, you see in the high flux state here, for example, you see broad emission lines. While in the low flux state, you do not see broad emission lines, you only see narrow emission lines. So this is kind of a change from type 1 to type 2 kind of object, and that is why the name changing look agents. And we have been lucky to observe some of these objects. One such agent is this NGC 4151, which is the brightest hard X-ray agent in the sky, and this is known to be a changing look. This is known to be a changing look agent. It shows very extreme variability in the optical as well as in the X-ray, and in the X-ray you see the spectral variability. And you see the huge soft X-ray variability and much less spectral variability in the harder X-rays. And this is thought to be due to the change in the obscuration or change in the X-ray absorption. And we already knew this, but then with AstroSat, because we have additionally UV, so we wanted to investigate what is happening to the UV emission, whether the UV emission is similarly obscured or similarly reddened. And here are the AstroSat observations. In fact, we had 5 sets of observations. I'm only showing 1 set of observation. And this is the only agents where we have the data from ultraviolet gratings here, the soft, the SXC, LXPC, and CZTI, in fact, all of the instruments. So therefore, we were able to study from the ultraviolet to all the way to hard X-rays. What we find is that by looking at the X-ray spectrum, we can figure it out how much is the X-ray obscuration from this side. By looking at the UV, we can find out how much is the UV reddening and how much material is required to redden redden and explain the data. What we find is the X-ray obscuration column is something like 100 times the UV obscuration column. This was actually a surprising thing. But then when we look at the torus, the obscurus X-ray absorption is generally thought to be caused by the torus, the dusty torus here. And if you think that the dusty torus is not a continuous medium, but it is made up of discrete blocks, dense material embedded in low density gas, in such a case we can actually explain our observations. In that case, because the X-ray source is much more compact, while the UV source is much more extended, so therefore even one dense blob can actually obscure the X-rays and giving rise to much higher obscuration column compared to the UV emission. And now if this is the situation, then these blobs would be moving around in the central engine. Therefore, sometimes obscuring, sometimes not obscuring, and explaining the changing look behavior in terms of change in the obscuration column, at least in these kind of objects. But then there are other kinds of changing look agents also. We also observed this another changing look agents, NGC 1566. So this one actually went into outburst in 2018, and here is the peak of the outburst. You see the flux was very low, and suddenly it increased by a factor of 100 or so, and then it declined. During the declining phase, we made 2 associated observations, target of opportunity observations, and we find very interesting results. So here are the UV, again the UV grating, and the SXC data, X-ray data, and these are the 2 observations. You see the change in the spectrum, huge change in the spectrum, huge change in the UV spectrum as well. We also utilize the existing XM Newton data, both near ultraviolet and X-rays. What we find, and then using these UV and X-ray data, we constructed the spectral energy distribution. And the most important result from this study is that the huge change in the spectrum from here to here. This is the before the outburst, and this is at the peak of the outburst. What is the most important change in the component? This is the soft X-ray excess component. It was the strongest component. It varied by more than a factor of 240. While in the it disappeared in the low flux state, or before it was not there before the outburst. So this we reported is the spectral transition in this AGN. So what might be happening that in the low flux state you have an accretion disk which probably goes close to the black hole, but in the high flux state the inner disk somehow gets converted into some kind of a warm corona, which is giving rise to the soft X-ray excess in this AGNs. What causes this kind of changes, spectral internal changes? That is still unknown, but some kind of stability is obviously should be responsible. But the time scales observed are much shorter compared to what we expect, for example, compared to viscous time scale. Another very important phenomena in AGNs nowadays is quasi-periodic eruptions. These are these eruptions are where the X-ray flux increases by an order of magnitude or so in a very short time scale, in an hour or in a few weeks. This is the discovery of one such AGN here, and the people have been discussing what is the origin, and people have come up with large number of models. For example, maybe some instabilities in the accretion disk, or the EMRI interaction of supermassive black hole with a much lower mass companion, maybe gravitational lensing, etc. But what is the real phenomena? That is not clear until a new discovery which was made with a number of satellites, and this seems to be related with the tidal disruption events. So let me explain what are these tidal disruption events. Every galaxy at the centers have a huge number of stars, and they are actually moving around their supermassive black holes. In that process, when due to the stellar interactions, some unlucky star may be made to go through the supermassive black hole. In such a situation, when a star actually reaches to the tidal radius, where the gravitational influence due to the supermassive black hole and self-gravity of the star actually balance. But below this radius, the immense gravitational force of the supermassive black hole dominates the self-gravity of the star, and the star gets distorted, it's broken, and then the stellar debris, some other part of the debris actually fall into the supermassive black hole, the other part escapes, and the debris falling onto here, they form an accretion disk, and therefore there is a huge change in the flux, in the optical UV X-ray flux. There was a tidal disruption event in 2019, and 4 years after the same tidal disruption event shown, the image is shown there, that started showing quasi-periodic eruptions. These eruptions were observed with Chandra, then the NICER, then SWIFT, and AstroSat. So this was the first connection that the quasi-periodic eruptions are somehow connected with the tidal disruption event. And when you look at the single quasi-periodic eruptions and look at how the spectrum actually evolving, and when you look at the spectrum of these things, they are simply like a black body. But their black body flux, their black body luminosity, and the temperature is changing in a particular fashion. Initially, the temperature is low, but then it increases. The luminosity also increases, the size also increases, and then towards the end, this cools down, and then finally it reduces. The temperature becomes lower, the size also becomes lower. So it is as if there is an accretion disk, and something actually strikes with the accretion disk, generating huge amount of energy, and that is producing the black body emission. And when it strikes, it increases the temperature because it gives the energy, and this thing actually expands, and this thing cools because of the radiation, and finally it starts contracting. It seems very similar to this is what is probably happening. So in the first side, the result of the TDE, a supermassive black hole torn apart a star and formed an accretion disk, and because of the debris are continuing to fall on, this accretion disk actually grows and expands. Then it expands so much that probably it intercepts the orbit of another stellar object like a normal star or maybe a black hole or something. Then this collision then causes the quasi-periodic eruptions because this thing has to orbit around the supermassive black hole. Therefore, you see nearly periodic eruptions which might be causing because of this collision. So here, thank you. So here I'll stop, and I'll leave with the list of results here.
Yeah, Gulab, I have just one queries first. That lag between X-ray and UV, you mentioned that the UV is lagging the X-ray.
Yes.
And you interpret that as like an reprocessing of X-ray. Now my question is the UV energy budget, is it smaller than X-ray?
Yeah. Much smaller.
Much smaller. So
Yes.
therefore the accretion disk contribution is negligible here?
No. Accretion, see, whenever we are talking about reprocessing, so what happens, those part of the X-ray is absorbed, and the
Correct.
temperature changes slightly. And then initially, without that, there will be an intrinsic disk emission.
Right.
And then after reprocessing, there is a slight increase in that.
Okay.
Yeah.
Thank you.
So actually, this location and geometry of the corona is not yet well understood, right? The systems where you see lag or delay between optical UV and X-rays, it prefers lamppost geometry.
So what is implied by this lag are kind of saying that the size of the disk, which essentially comes from the time delay between the corona and where the UV is arising, that is larger by a factor of 3 compared to what is predicted by the standard disk model.
Yeah.
So either the disk is large or the corona is not very close to the center of the disk, but it is much further away, maybe 50 or 60 RG.
Yeah.
Then that light travel time, because it increases, and also because of the strong gravity, the bending of light, that also increases time. So overall, this way one can possibly
Agreed.
understand.
So the systems where you do not see lag or delay between
Yes.
this, so that means it prefers sandwich geometry than lamppost geometry?
In that is also possible. In fact, we studied with XMM Newton. So in some cases, if the corona is very close to the black hole, then the coronal emission is, because of the gravitational light bending, is focused in the innermost regions. So the outer regions are not that much illuminated. The middle regions and the outer regions are not that much illuminated. So therefore, we don't see the lag, no reprocessing at all.
Okay. So yeah, Gulab, you mentioned that dense blobs can be the reason for changing look phenomena. Dense blobs. Yeah, so where are those blobs coming from, and what can be the origin for such dense blob?
See, in the changing look phenomena, what we see, okay, so there are two types of changing look phenomena. One is due to the change in the obscuration. So the obscuration change, because the X-ray obscuration is generally thought to be due to the torus. And if the torus is made up of discrete blobs, those blobs, the movement of those blobs will change the amount of obscuration. So that will cause the changing obscuration scenario.
Okay, last question here.
Yeah,
Okay.
there were some repetitive bursts which you showed in one EGN with very shorter time scales. So how many such EGNs have been? Because is it that we don't observe them for continuous things, we don't have such EGNs discovered, or what is?
EROSITA has discovered, and it is discovering newer and newer objects. I think there are 7, 8 such, not many objects, but 7 or 8 such objects already have been discovered.
So longer continuous observations will help.
That's right. The detectors with large sky coverage, with doing survey, certainly will discover many more.
Okay, thank you very much. Anyway, I want to ask one last question. Okay, so this is continuing what I discussed with Ranjay. We are the only few of the workers who have used all the 4 instruments of the AstroSat and 3 X-ray instruments. Now, if you want to bring down the systematic of 3 X-ray instruments down to the counting statistics level, how much work is there? Do you have a feel of it?
We have to have, first of all, a team, and then the information from the instrument teams. When we are, not really, not really. We don't have the full information. Even for example, the SXT. The SXT response was built by the lesser team. And when we want to improve, you will have to have that information. What are exactly the parameters used, or how they did that, and then play around that.
What is the magnitude of the work?
I would say if all the information is made available, it's a question of 3 months.
Wow,
3 months.
okay, then we should be doing. Okay.
Just
Anyway,
SXT.
thank you, Gulab. It's
Yes.
wonderful talk. Okay, let's thank him again. Okay, now I hand over to the.
Let's give a big thanks to Professor Rao for coordinating this session.